Good evening, everyone. Welcome. Before we begin, I'd like to share a land acknowledgement. The indigenous creation myth of Turtle Island describes an assortment of species working together to build a continental landmass on the back of Turtle in order to create a place for Sky Woman to touch down as she falls from Sky Woman. We wish to invoke this collective act of world building as one aspect of our acknowledgement that we sit on the stolen lands of the Peoria, Kaskaskia, Piankashaw, Wea, Miami, Mascoutin, Odawa, Sauk, Muskaki, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. This is a starting place from which to invent new stories for the new worlds that we will build together as we collectively and individually decolonize and unsettle ourselves. Welcome again. My name is Joseph Altschuler, assistant professor here at the Illinois School of Architecture and chair of the Lecture and Exhibitions Committee. And it is my distinct pleasure to welcome you to tonight's event. Also, happy Eclipse Day. I think this might be the first Theis lecture ever on an eclipse, which is another, I think, milestone to take note of. It was great to see many of you outside on the South Quad reveling in the orbit of our planets, moons, and sun. So before I begin, I do want to make one quick announcement, which is we have a special bonus lecture event, less of a lecture, more of a conversation that will be happening this Wednesday after studio at 6 p.m. The event is called 3D Mediations. 3D stands for 2 directors and 1 dean. We'll have the pleasure of convening for, I think, the first time, our own director of the School of Architecture alongside the director of the University of Illinois at Chicago School of Architecture and the dean of the College of Architecture at IIT for a conversation about the future of architecture schools, about the future challenges and opportunities in architectural pedagogy. And it will also be the first of 3 events that will be visiting all of these schools. So we'll invite you to come with us in future semesters when we visit UIC and IIT to really kind of propagate a broader conversation about what we're doing and how we might be able to do it better together. So I really encourage you to come back on Wednesday evening at 6 p.m. for this bonus event, 3D Mediations. It should be a really exciting conversation, and we'll ask our own director and the director and dean of UIC and IIT some hard questions, I think, about the future of pedagogy. So really encourage you to come out. It's going to be super awesome, if I do say so myself. And that brings us to tonight. And this will be the sort of final lecture of our curated series, Building Affinities. Affinities connotes a natural attraction to a person, thing, or idea. The lecture series explores the intimate attractions among architecture, people, and the expanded environment. What affinities might we have for our buildings, and how can we build new affinities and affinity groups through empathic, entangled architectural production that cultivates a shared sense of belonging? And tonight, it is my distinct pleasure to invite my colleague, Professor Abbas Ahmed-Mansour, to introduce tonight's speaker.
Thank you very much, Professor Altschuler. Good evening, everyone, and welcome. I'll read a brief statement about the Theis lectures, and then I'll introduce our speaker for this evening. This evening's lecture is supported by the Michael J. Theis Memorial Fund. The fund was created to honor Mr. Theis, his memory, and his interest in integrated architectural and engineering design of buildings. Mr. Theis received his bachelor's degree in 1970 and a master's of science in architectural engineering in 1971 from our School of Architecture. His career as an engineer spanned over 2 decades, many of which was spent in New York. His work included design of tall and distinctive buildings, as well as restorations and renovations. Michael J. Theis Memorial Fund is used to support events at our school to encourage and promote the study of our structures in architecture, while facilitating interaction between students and practicing architects and structural engineers. At this time, I'd like to recognize Michael's wife, Cindy Theis, and his personal friend, Mr. Ron Johnson, I believe they were going to join us on Zoom. I'm not sure if they're on Zoom yet or not, but in any case, we would like to extend our appreciation to both of them for their support to create this fund and to support our students. Now it's my privilege to introduce a very fitting speaker for this evening's Theis lecture. Matt Streid here at Magnuson Clemensic Associates, a highly regarded firm based in Chicago. Matt is based in Seattle. Matt is from the Chicago office. He's a principal at the firm and a leader in their office and life science specialist group. He's a graduate of the Illinois School of Architecture, having received his bachelor's degree in 2005 and his master's degree in 2007 with specialization. His design experience ranges from low-rise, multi-building office campuses to complex high-rise office and mixed-use projects throughout the United States. Matt has worked on projects with many notable alumni firms of the school, including Studio Gang, Kelly Clark Partners, Picard Chilton, and Miller Hall. In addition to being a project manager on the recently opened Salesforce Tower in Chicago, he has applied his expertise to design of many signature structures such as Seattle's Amazon Block 20, Boston's Back Bay Station, and numerous heavy timber office buildings. Please give a warm welcome to this evening's speaker, Matt Streid.
All right, everyone can hear me back there again? Thank you very much. It's an honor to be invited back here to lecture. I give a good amount of presentations, but I admit I'm a bit more nervous being on the other side of this classroom. It's kind of scary to think that it was over 20 years ago that I was a freshman sitting in this classroom in Arch 101 back in 2001. I'm starting to recognize that I'm on the other side of the fence now and getting pretty old, but I really appreciate it. And glad to be here today. Start. So I was optimistic this was going to be a picture that I took this afternoon, but it didn't turn out that way. I had to steal this one really quickly from Google to kick this off in honor of today being the day of the solar eclipse. But there's lots of questions in the world that we wonder. Why is there a solar eclipse? Why is the sky blue? Why is the grass green? You get to buildings and you ask the question, why is there a column here? There's a scenario where I get a little hesitant because maybe my architect's not thinking and realizing that we have a structure that needs to be supported. We have to respect the realities of gravity and the constraints. But it's a complex question because we can do this without a column here. But there's layers to understanding the constraints of a project. What are the budgetary constraints? What are the site constraints? And so sometimes there's scenarios where we have to have a column here, and sometimes there's scenarios where we can't do that. And so there's not direct answers to those scientific questions, and there's a lot of background. And not to scare you off that, I'm going to say we have to put columns anywhere. The big benefit that I have of coming from an architecture background is I have a lot of respect for the vision of the architects. And I think that manifests also through a lot of my colleagues and a lot of our industry to realize that what we're doing as structural engineers is trying to realize the vision of architects. And how can we do that in a way that creates the dream and the space that you've realized, that you want to realize, and make sure that it's happened, make sure that it's buildable. And so just like as if I was on a project with you, I'll build the trust that there are scenarios where we can have amazing, beautiful spaces like the Perlman Art Center with Rex. It's in New York City, just opened up recently, adjacent to the World Trade Center site. It's an amazing feat of structural ingenuity and architecture, and the space that it creates as you enter this is really amazing. And I'm kind of embarrassed by this quote that when I was interviewed for the Ricker report few years ago now. It was like a 3-page article, and like in big bold letters on the front page, it said, Matt Streid quotes, "Physics is physics." And I was like, oh man, that's the quote that they took him on this. And well, that's true, right? Like the point of that statement was that physics is physics, and any engineer or person can solve a problem. We understand gravity, we understand lateral forces, but how do we solve problems in unique ways for any given project? How do we work with the team to collaboratively solve the challenges that are on any given project? So the idea being that what we're doing as structural engineers is more than just putting columns and beams and sizing things. We're working as a team to understand what it's going to take to realize your vision and make sure that it works. We want to embrace ambitious architecture, but need to make sure that it's actually buildable, or otherwise that dream might not be realized. So at MK, we're very fortunate to get to work on a lot of amazing projects with a lot of amazing people, from high-rise, the tallest building in any given city, to cultural gems, convention centers, stadiums. There's a lot of opportunities that we have. One of our senior partners once said that we're very fortunate to get to work on several once-in-a-lifetime projects at MK, because we have been recognized by architects, world-leading architects know that we have their best interests in mind. Again, anyone can solve a problem, but how can we do it in a way that actually executes it to make sure that we're able to realize our vision within the constraints of gravity and budget? So sometimes that vision's not quite as clear as you might think. This is a sketch from Frank Gehry of the Experience Music project that we did. And sometimes that vision actually does just become the reality. Sometimes it is just a matter of kind of forcing the structure into that vision. And that's not a knock on this, not to my colleagues, not to Frank Gehry, saying like, here we just kind of a little bit more brute force. We're literally going to bend the steel to just create exactly the form that we saw in that sketch. But really, it's that idea of how are we working with you to solve the problem? And on this case with the Experience Music project, we were pioneering the idea of three-dimensional modeling and delivery. This was 3 decades ago, well before we had Revit and 3D modeling. All of this project was delivered to the contractor by giving them 3D models and sharing like things that we're still this day and age struggling to do shop drawings in 3 dimensions. So the idea is solving the problem, whether it's kind of forcing the hand of, all right, we're going to match the architecture, but we're going to make sure that it's actually a buildable structure. And there's visions like this, kind of more softer, realistic vision, not that wild sketch of Frank Gehry, but just a beautiful watercolor. This is a very early sketch from Tony Marchese, a graduate of this program, with Picard Chilton. They're a great architecture firm out of New Haven that we've done a lot of work with. This is in Cambridge, just north of the MIT campus. I do a lot of work on the East Coast. I travel there quite regularly. And in this vision, Picard Chilton saw this idea of how do we take a traditional office space and kind of expand out to create these views, like the views from this angle where these kind of pieces, these cantilevers are, have amazing views out to Boston, over down the Charles River. And they wanted to create a space, like these early visions. And you can see the trees, the open terraces. They were trying to get people out of their office space, and how do they kind of get to a unique amenity within the building. And in my mind, this is a cool instance where the project's even better than that sketch in my mind. The way that cantilevers are actually bigger than what they were in those initial schemes. And so what does it take to actually implement that and realize that space that Picard Chilton envisioned? And this could have ultimately had these windows knocked out and be acting as terraces. There ended up being a tenant who moved in and wanted to utilize those spaces in their own dynamic way. But the premise is, how do we create that space that's kind of a breakout? So very early on, we are producing iterations, dozens of concepts to understand, okay, if we're going to do these large cantilevers, initially that space wanted to be wide open, right? Like that idea was you're walking out there and you're looking out over the city of Cambridge and Boston. And so we want to have as clear view as possible. So we said, well, we can do cantilever beams, but those beams are going to be really deep. And we're particularly pinched for height in Cambridge. There's a very strict height limit. We're trying to maximize the floor plate for the owner to make their money. And we couldn't afford to have those big deep beams. And we looked at the idea of doing a sky hook. What if we put a really big one at the top and hang everything down? But again, that floor would have a really deep beam that was crossing over. So then we start studying the idea of diagonals. And do we want to have one really big diagonal, which that kind of in each given space, you see this kind of large diagonal cutting through. Or do we want to do a series of smaller diagonals? And maybe that gives you flexibility to cut out certain floors. The point of this series of iterations is working with the architectural team to say, here's different ways that we can support it, but more importantly, in this case, giving this to early contractors and to the owner to price it and understand what's the more buildable solution. And what that gives you is the most economical solution that made sense from a structural efficiency standpoint. Doing that series of 3 diagonals at each floor gave us the opportunity to have a smaller diagonal. I think these were 2.5 or 3 inch diameter, but the next layer of that solution is saying, well, we've got these diagonals that are supporting almost 30-foot cantilevers. And in order to make them fire rated, we'd have to enclose it, whether intumescent paint, like that's the secret sauce in all your designs, I'm sure. It's very expensive. So do you wrap it and you do things that start to inflate the size of those diagonals? And so what we said is, well, why don't we, in principle, we will design the beams to take the strength, the demand of these cantilevers reaching out over 30 feet can technically satisfy the code without these diagonals. But without these diagonals, they're going to sag 5 inches, 6 inches, which is obviously not acceptable from a serviceability standpoint. So we implement these diagonals. So these diagonals are really doing all the work. There's a tremendous load path that's dragging these back into the core. But by doing that, we don't have to fire rate these diagonals because they're technically not required to make the building stand up. And this tenant that moved in took each one of those. We ended up calling them the Jenga pieces, which I don't know if Tony appreciated that or not. But each one of those 3 Jenga pieces had these 2-story spaces created, again, with these expressive views out. And actually the view, I don't have any good pictures looking out because that's the expanse of 2 stories of glass. But of course, I'm trying to show you my structure. This is another project with Picard Chilton, this time in Seattle. And this is an example of trying to use how can we note that the structure is going to be expressed at the base of this high rise. If any of you have been to downtown Seattle, it's on a very steep slope down to the Sound. And with that, there's a lot of different solutions that are implemented. And what Picard Chilton tried to do here was recognize that they wanted the public to be able to embrace the bottom of that high rise. How is it interacted? And if we lift the base of this high rise up, it gives the opportunity for interchangeable programs. Are there different retailers that can come and go within that space? Are there presentations, concerts that are put on in this open public space? So they wanted to take that idea of lifting up this high rise. So that's where we need to come in and understand very early on in the concepts, how are we embracing that concept, and right off the bat understanding that we've got a 40-story building above this. There's a lot of load here. We need to understand how that's interfacing with the ground plane, because that's the architectural expression, is where these columns meet the ground. That's where the public's interacting. And so that node that you're seeing here is fundamental to the early concepts. As structural engineers, we like work points. We like things to be concentric. The center line of these columns wants to be the center line of their support. And the reality is, for a deep like the foundation system of this building and these work points, that really is centered well below the ground plane of where people are standing when you take into account the buildup of what it takes to waterproof and landscape these plazas. So we need to understand really early on, are you okay if the work point actually has a gap in between the columns coming up and there's not that moment where the columns intersect? And so can we iterate through did I skip one there? Iterate through those work points to understand what you're actually touching and feeling. And as an office building, it's in most markets, very geographically driven, but in most markets in the US, you're going to have a steel framed office building for a variety of reasons I won't go into today. but noting that this is a steel structure coming down, Picard Children did not want to have traditional like stainless steel cladding. They wanted to have a column, like a cladding around these columns that people could touch and feel because they wanted people to be interacting with this space. And so recognizing that as a steel building, the more economical way to build that was to use precast. But precast is also, not the touch and feel that you want. And so from a cost perspective, we recognize, what if we pre-install precast columns? You're seeing them wrapped up there. In the shops, they're delivered that way. So we get rid of 80% of the column is prefabricated, but down where the people are interacting, like at this lower steel base, that's all cast in place concrete to give you that opportunity to feel the real concrete and not the joints of a precast connection, which really delivered quite a beautiful space in Seattle. Again, all at the base of a 40-story building. So going back to this entry slide, so 111 South Wacker is where our office is located. That's where I go every day for work. We were the engineers on this project. And as I said, there's scenarios where we didn't have to have all the columns here. What's the right solution for this project? Really, part of the vision, I won't say that, so that's designed by Getch Partners, 111 South Wacker, not that they intentionally envisioned this, but it was that idea of how do you lift that base? Very similar to what PCA did in Seattle. Rainier Tower in Seattle is actually where our headquarters is based here, a project that we did with Minoru Yamasaki in the 70s. This was a scenario where the developer had a certain amount of square footage that they could utilize. There was no height limit. So they said, well, everyone wants views in Seattle. You have amazing views out over the Sound in the Olympics, that they wanted to raise the building up. And so they challenged us with what's the way to just take all that square footage and push it up. That concept was in the very initial phases of design for 111 South Wacker. So as we progress through the design, you can see where all of these columns at the perimeter are coming in. It's kind of like the steel version. That project you just saw in Seattle at Rainier Tower is a tapered, very robustly pretension slab that brings all those loads down into that core. So here were ideas of doing steel columns, framing that in. But that line is September 11th, 2001, where everyone kind of turned their thoughts on what are we really doing with the future of high-rise buildings. People were afraid to be going back into high-rise buildings. And so you can very quickly see, quite literally, the step down, not only in the height, but also the robustness of that base. From an engineering perspective, they're equally as safe, right? We can solve these problems equally, whether it's any of these iterations on the left or on the right, but the public, people like to feel comfortable and safe. And after 9/11, that was something that had to be thought about a little bit differently. And so we progressed through those schemes. So that's where, again, that column's not required, but it actually kind of became a necessity to help the feel of the building be appropriate for that time. And very simply, just taking all those perimeter columns, instead of 16 columns around the perimeter, we reduced them down to 8 columns. So there's just 2 columns on each facade with a rather notable cantilever at each of the corners that's created through these kind of V shapes at the base of the building. The cool feature of this lobby space relative to space that's created is the underside of that curvature. You can see much better in the other picture, is actually the underside of the parking ramp. The parking ramp's just a couple feet above that lobby ceiling. So you actually drive in the building on the left here and wrap around up 4 stories to get to the first parking level up above the lobby. 150 North Riverside, hopefully it's something maybe you're not quite seeing in the architectural world, in the engineering world. It got a good amount of headlines for the very challenging structural solution that was implemented. But the reason this follows that 111 South Wacker image is that Jim Getch, the partner at Getch Partners, who designed 111 South Wacker, I think like any architect, architects don't necessarily want to repeat visions, right? You want to apply the right solution to the right project, to the right site. And having that kind of mindset of how can we do this tapered building, 150 North Riverside presented itself as the perfect solution that needed it. It was a necessity to thread this building in between the railway lines. In this case, the entire building, so again, those models you saw on 111, all of the perimeter columns are sloping down back into the core. So if you imagine the loads that are coming down on a 50-story building, millions and millions of pounds, right? We're talking 5,000, 6,000, 8,000 kips of load, and then turning that at nearly a 45-degree angle. That's ramping up those loads again by another 35%. And the real challenge, even though you see the river on the right, we could have pulled off putting those columns all the way down through the river. It would have been very challenging, but the columns on the left-hand side had to be transferred because there's railroad tracks directly below this. And so from an engineering perspective, if we chop out the legs on one side of the building, it's just going to want to lean over, and that's putting a tremendous amount of force onto our lateral system that's there for wind loads. And now just recently, Chicago also has seismic loads, but for lateral loads. But now we've got a big gravity-induced drift that we're kicking in. So it's actually the best structural solution to chop out the leg on the other side to balance everything out. That creates a tremendous amount of force. These columns, these diagonals are the largest shape available, largest regularly rolled shape available in the world. It's a W36 by 925 in grade 80. So the highest grade steel that just came on the market, available in the world, rolled in Luxembourg. I think I said readily available, but Luxembourg high grade steel is not readily available. Arcelor will be upset that I said that. It's available. But not only is it the largest shape in the world, but they're actually back to back. There's two of them. So these members are about 2,000 pounds per foot in these diagonals, and all that force is balanced by that tension tie going across. And what you can start to see, actually you don't see it as well in this image, is that the aspect ratio on this building, on a typical high-rise building, if we're at 8:1, 10:1, aspect ratio being right, like the width of my lateral system, we don't care so much about the perimeter columns. Like our core is what's doing all the resistance to those lateral loads. Something in that 10:1, that's like a no-brainer, nice and straightforward. We often get into like a 12:1. People keep getting more aggressive. Our sites get more constrained. But this project has a 20:1 aspect ratio, which means that core is extremely tight and it wants to be much wider. So in this project, again, there's a lengthy engineering lecture I could give on it. We actually implemented tuned liquid dampers up at the top of the building to help counteract this sway, right? So as the building's swaying one way, the sloshing damper at the top's going the other way to counter it. So a lot of really challenging engineering tasks at hand for this project. But at the end of the day, not only was it solving the problem, the Chicago River is at a high premium. People want to live and work along the river, and there's not very many sites left. So it was the solution to work to get to build on this site, but it also created a beautiful public space for people to walk along. There's a restaurant there along the river that's a really amazing experience, all created by how we're trying to solve that structural challenge. Real quickly, I'll touch on the easier solution to the problem of that aspect ratio. Salesforce Tower also initially has something like a 20:1 aspect ratio, but instead of going heroics of sloping the columns and putting in a sloshing damper at the top of that, the more idealized structural solution that starts to have architectural and coordination implications is to introduce outriggers, right? Just widening my stance, like if my arms are these big trusses, so now I'm engaging those perimeter columns. But what that does is these are 2-story deep trusses that we need structurally somewhere ideally around the 2/3 point of the building. And so very early in coordination, we raise our hand and say, look, we're going to need outriggers on this project. It's the most cost-effective, efficient way to solve our structural challenges. So what can the architectural and mechanical teams do with that? And so that's what that diagram on the right is highlighting. That's where we put our 2-story mechanical floor to service a 1.4 million square foot, 60-story office building. You need to have very large mechanical equipment. There's tiering in the elevator schemes. So this is that transition between the mid-rise and the high-rise elevator bank. It's also the central kind of distribution of the mechanical system. So again, working with the team to understand where's where's that spot that we can work with them, and also agreeing on that early on. The structure's almost always out in front of the architecture in terms of going out to get bid and start construction. So we need to lock in these decisions very early on. So we need to have buy-in from the whole team to really understand that. And just highlighting really quick from an architectural perspective, down here, you can see where the louvers were at for the intake system. So that two-story mechanical space, there's large intake and exhaust feeding that. And it was a really beautiful architectural solution by Pelly Park, where they created, instead of just buying louvers off the shelf that you see in a lot of high-rise buildings, they created a custom kind of offset glass. So the plenum is actually horizontally, so the air is kind of going in between the glass and going sideways. And it really is, I mean, this is technically a rendering, but I assure you that the real building is now built and occupied. Really did a good job of concealing that two-story space. So we're starting to kind of change the scale of what we're talking about in terms of engineering solutions. This is another project with Picard Chilton. I find myself very fortunate to work with them a lot. They're great in their understanding of how we interact as a team and we work together to solve challenges. This is 325 Main, it's the new Google headquarters in Cambridge, or their northeast headquarters, again, just north of the MIT campus, where they occupy these two buildings, left and the right, both owned by the same developer. But the idea was they wanted to maintain operations and use of their space. They put a lot of money into the interior architecture of their current space here on the left-hand side. And so we were going to build our new building adjacent to it and kind of consume and engage that. Maybe consume is not quite the right word, but we were engaging with them. We took off that whole facade, that brick facade you can see running into the page here, that was peeled back. And our new structure from levels 4 through 11 interface with that. And so we have a series of ramps and stairs that are helping create all those offsets. But again, going back to these very preliminary concepts of how are we going to solve this problem? There's lots of different solutions. Again, we're going through dozens of iterations to understand architecturally. If we do this on the left, we can have a sloping column. It's a rather subtle slope, so it's not as impactful on the interior architecture. But in this case, the cantilever is getting pretty aggressive on the left-hand side. So we are punching through the base of that existing building. On the right-hand side, we're staying out of that existing building, but we're implementing large trusses. And so those trusses are a little bit more impactful on the space. Ultimately, we did some variation of that truss that has a large diagonal going through that is literally hanging up against the existing building. We kind of at some point called it the backpack, which is kind of hanging off the side of our building. But what that allowed us to do is, as that space was previously a roof, an unoccupied membrane roof of an old 1980s waffle slab building, we ended up going in there and putting carbon fiber wrap on the underside of those waffle slabs. We actually had to do some on the top side as well. And with the heroic efforts of some iron workers who are the most fearless people you will meet, you can see this guy hanging out on the right-hand side, hang that steel out over the side. And what that creates is a space in a place that previously did not exist, in the context of this stair is built on that existing roof and that terrace is on the existing roof, and everything is jointed as it combines our building. So our new structure is actually the ceiling of this space, and all of the floor and the support of the stair is on that existing stair, or on that existing roof. So again, the creative problem solving of how we're going to reinforce this, how we're going to hang our system to make this a unique, like a 100% column-free space, because everything about this volume is supported up and to the left of the existing building. So hopefully you've seen, if not in person, you should try to see them in person, the Amazon spheres also in Seattle. It's, you know, the kind of very clear definition of structure becoming the architecture, and 100% important to integrate with the architect to understand what is the vision that they're trying to create, and at the same time, what is a buildable solution that is structurally efficient to realize this dream. This is another project with MBBJ in Seattle. In their initial concepts, the architects liked this lamella form for the spheres. That was kind of the front runner in their initial concepts. They knew they wanted, I guess just stepping back, if you haven't seen the spheres, the idea is it's an amenity space for the employees of Amazon. There's small portions of it that are open to the public. I was fortunate to be able to go in there before it was fully turned over, but it was built out. It is an amazing space, but it's basically a living form. Like there's plants from all over the world. There's full growth trees. It's quite an incredible space. And then that was, you know, this idea of a kind of geodesic dome. And so that's what led to these studies of how are these three spheres going to interact with each other. So architecturally, they liked this lamella form initially, but what we recognize is that all of the intersections of those angles create unique shapes. Like how are we infilling that with glass? Like what is, that's actually not a very repeatable form, even though it looks like a very uniform, clean, like I found the lamella shape, that's like, look at this nice smooth sphere. It's actually a lot of lacking repetition in how that would be created. The central image is maybe the more structurally clean shape. It's just a repeated hectagon, and you know that's something that we can rationalize very quickly. And then, or is it somewhere outside of that, and it's just a purely organic form? But there's a lot of inefficiencies in that. And through studies and conversations, people started to recognize the Catalan solids. There's 13 polyhedron Catalan solids. I think there's like 11 of them formed here, but it's effectively a series of shapes that are repeated to make a solid. So not necessarily purely spherical, but as you can see through these iterations, conceptually, they're creating a volume by repeating a consistent shape. Ultimately, the team settled on the pentagon Catalan was the shape that was kind of the best compromise of being, getting that spherical shape. And so how can we start building on that? And so as we start very early on to iterate, what can we do to infill that pentagon? The initial concepts were dozens of pages like this. I admittedly didn't personally go through all these studies, but my colleagues who worked on this project said there were on the order of thousands of shapes that we were using to fill that Catalan, that had to find that balance between what was the right architectural expression. These are going to be very interfacing with the user. People are going to be up close to these, touching these. It wants to have a beautiful aesthetic. It's a very iconic structure. And there also has to be some structural efficiencies, which led to the selection of this Catalan shape, or shape within the Catalan, that was the right balance of giving the architect the curvatures that they wanted. And ultimately what was settled on in the design was that this primary shape formed by all these pentagonal Catalans was going to be the exterior structure, and everything on the inside would actually be supported on a series of kind of cut plates. Like there's some concrete cores, some columns, and a series of round plates that obviously change size as you go up and down in the sphere, and they're carved around that. But ultimately, the gravity system of this building is all on the inside of it, and then the sphere is around the outside. So with that, we write our Grasshopper scripts that are actually used to iterate on all those other thousands, maybe it was down to hundreds at that point, and dozens of shapes to see where are there hotspots, are there different shapes, how can we change the geometry of this selected shape to make the most structurally efficient, uniform condition. Because what we don't want to have is a series of really high stress concentrations at one place and really low stress concentrations at another place, because all this wants to look uniform. We don't want to have big bulky sections and smaller sections, and we don't want to use those big bulky sections where it's not necessary because the architect wants uniformity. So how can we use those scripts running through our analysis software that were directly linked into MBBJ's Rhino model, so we could interchange, very quick exchange of modeling to make sure that we're economizing the structure, to make sure that it's buildable and within budget. I think this project wasn't technically within budget, but Jeff Bezos has some money, so it worked out. What we care about is still trying to aspire for efficiency, which we got here in the sense of how can we fabricate this with as much readily available shapes. So these blue shapes are already rolled HSS shapes, so square HSS, hollow steel sections, and then they're rolled. You can put them through a rolling press that gives them that curvature. And then the red elements are just made out of built up plates. Something to the effect of this, where on that top image you're seeing before it's been polished and ground down and painted. But that lower horizontal member is that HSS, which is out of the AISC manual. And the rest of those kind of red pieces were built out of the built up plate, ultimately giving you this form. And you can see the scaffolding on the inside that was used to build up and support the erection of this, used to support that interior concrete frame. But it's that same shape repeated around the entire sphere on each one of those three spheres, creating not only a beautiful structure or piece of architecture, on the outside that the public can engage and see. And you can see that next level of glass refinement. How did they break that up? And still, I don't have the number, but it's still a very repeated number of glass pieces. There was not a lot of custom glass per se. It was repeated sizes of these triangular glass infill pieces. But what was created on the inside is really the beauty of this architecture. Again, where you're up close, you're gonna get a sense of scale on those catalans. When you see the people here, you wanted to have that. Not only, of course, there's an AESS finish, like what's the quality of the craftsmanship and the steel fabrication, but the geometry and the coordination of how those pieces are made really mattered, because people are going to feel that space. And you can see the columns and the floor plates that are all held back from that exterior structure. Also, to recognize that buildings have utilities, right? Like even in the spheres, a quite wild and imaginative structure, there's still a central core with elevators, stairs, mechanical systems, but engaging these are structural walls for us, but how can we cast into the forms, shapes that help to mimic the kind of living aspect of what this building can offer? And really, it created spaces that are unlike any other spaces that you've been in buildings. The bird's nest is this unique point in time, this moment that someone gets to experience where it is just kind of you floating in the trees despite being in the middle of an urban environment. And that was the dream from Jeff Bezos, to say that I have my employees, that I want to give them a space that is their own, where they can go and just have a reprieve and get away from the office environment. A structure you've seen is the Lincoln Park Zoo Pavilion with Jeannie Gang. This project is another great example of the structure becoming the architecture, and that process of understanding what is the vision and how can we economize that in a buildable way. This is a project that did not have some exorbitant budget. There was a fund that we were working around to try to create a buildable space that the community could engage with. And there's kind of two key points through the example of this project. iterating for structural efficiency, very much like what we just kind of talked through with the spheres, and what's the most efficient structure to make it economical, but also how's it going to get built? Like how are you taking three-dimensional build or curvature on wood pieces, and how is that detailed? So again, building like this is a much more straightforward model than what we had to do with the spheres, but that one of the initial concepts on the left, the shapes, if you look kind of from 1,000 feet, like they look like they're pretty much the same general curvature, but they're a bigger curvature. And what that did is naturally create two big arches. So this wanted to have a lot of heavy structure on those kind of big, heavy red and blue lines, and everything else could have been light. But again, there's not an efficiency there. So what we did is start, again, running through some Grasshopper scripts, interchanging with Studio Gang's model to see how can we ever so slightly change the angles on these to try to get some more uniform stress distribution that allows us to create the geometry and realize that vision. So the other aspect being the constructability and how is it executed. We started working with Jeannie to understand how do we want to approach forming wood like this? Like what industries work with wood and curved wood? And so we talked to the boating industry, and it turns out a lot of the boating industry is more two-dimensional curvature and how they integrate the wood into their shipbuilding or boat building. And so actually most of the ideas came from the furniture world. So there's a lot of really amazing things that are done on the scale of furniture building that was implemented here to start to realize how can we form the wood three-dimensionally. So you can see it curving over this formwork that was implemented with the through rods kind of holding that wettened wood in place while it cures and sets up. But it's also bending in plan. You can kind of get a feel for it, that it's bending. So we've got three-dimensional curvature in that. And I believe that it's just these three pieces that are repeated over and over to create this structure. So you can kind of see the shorter piece on the bottom right, the longer piece on the left, and that medium piece in the middle. And that's the shape that was repeated over and over to create that. So again, once we got the form, how are we going to build this? There were a lot of iterations with the fabricator, the wood fabricator, that shop. We went in there with Jeannie Gang to see what can they do and experiment that. And we kind of ended up with this is what we wanted to do, and they were able to build that. And so we can repeat those three pieces over and over again, making that a space that is a very unique, once-in-a-lifetime experience to walk through the pavilions. It's one of the most, if not the most, photographed site in Chicago, used for wedding backgrounds, yoga classes. I've taken my kids out there to take pictures of it. But I think the other key aspects of understanding what's happening here is how does this meet the ground, right? People are going to interact with every piece of this. Kids are climbing through it. People are looking down, feeling it. And so understanding the details of how these pin connections engage the ground was very important to Studio Gang to understand. And also the jointing and the connections. There's some aspect where you might want to just conceal everything. That's not where Studio Gang's at. They like to embrace and accept the structure and the connections, but then be mindful of that. How are the connections aligning? You don't want to have a bunch of staggered connections, or maybe you do, right? But the point is to think about that. Like the form is just the very beginning of the space that you're trying to create. And how are you executing that? How are you connecting it? How are you building it? We're learning now, how do you maintain it? It's been in place for over 10 years now. And we're going back through and implementing a new maintenance program on it to look at all the different, we've currently taken off all the plastic shells just to do some maintenance. Everything's fine, and it has to be up and running by photography season here in a month. But again, just thinking through how all these parts and pieces fit together. Get near the end here. So it wouldn't be an engineering presentation if I didn't try to rationalize this. We're just inherent problem solvers and want to just have a clear explanation for why things are what they are. So this is a Venn diagram that we put together for a project proposal, like pursuing with the client. trying to say how we work. And this is kind of the epitome of who we are at MK, and certainly who I am as an engineer, to build that trust with your team, because you want them to respect the fact that I have your best interest in mind, and I'm not saying something because I personally want a column there. That's because gravity's telling me that's where a column wants to be. That's where the existing conditions are telling us there's a column that wants to be. But the other key piece is the proactive communication, the idea of how you don't want to be a reactive engineer and really design consultant. Like it's applicable to any industry really, right? Like there's one way that I can come and sit in a room and wait for the architect or the owner to just tell us exactly what they want, and then I can react to it and infill the structure, or we can be proactive and come to the table with solutions and ideas. Here's the constraints on this site. How can you work around these constraints? This is a bad zone to land a column. Is there an opportunity to move this somewhere else? And how does that start to influence the solution and the idea of running through the challenges? That's, where's the heart of the problem and how can we get there first and solve that major challenge on any given project, and then let the rest of the project unfold. But we really need to understand right from the outshoot, what is the biggest challenge? And that also manifests itself in construction. Like when there's a problem, something's not right, something's not how we thought it would be, we can't shy away. We need to run to that problem and solve it and execute it. And the key is really just to be proactive. So I'm going to end on two quick high-rise buildings, because at the end of the day, that's who I am. I'm a high-rise guy. There's a lot of beauty in what you can do on those small scales of the cultural projects. Hopefully you also saw that there's beauty in what you can do even on large-scale projects, how you can create amazing space in high-rise buildings. But aside from collaboration and trust giving you good architectural spaces, there's also a lot of importance in that trust in other challenges that we face in the built environment. This is Texas Tower in Houston, the project I worked on with Pelly Clark. And here, the emphasis of why trust worked is because all of a sudden the developer landed a major tenant who was going to occupy this building, but only if it could be delivered and occupied in a certain time frame, which meant we had to immediately go and get foundations in the ground. So they quite literally we were in the middle of SD when they landed that deal, and we skipped DD entirely. It's the only project where I had where we just went from SD to CDs, and by the end of SD, they were installing foundations. And the reason that trust and collaboration matters is we have to communicate to the team, here are the things that can't change, and if you need to change them, tell me now. And so we outline, here's the most critical path information that we need in order to implement the foundations. There's things we can change later, but here's the ABC different things that you can't change. So we need to really quickly, early in schematic design, understand that we're on the same page in order to execute this project, which really did go off without a hitch, and it's really successful, beautiful building in Houston. And lastly, ironically, I'm showing a building that never got built. I've been very fortunate that nearly every building that I've worked on has been built. But this project was down in Tampa, I don't know, 6, 7, 8 years ago, maybe now. It stopped after SD, but it was a very pivotal point for me as a young project manager. I was a project manager, and Ron Klemenczyk, our CEO, was the principal in charge on the project. And two takeaways from this project is he flies all over the world constantly. I fly a decent amount, not quite as much as him. And we met in Tampa for this project for one project meeting. And the client asked something, and I was kind of back on my heels. And he, who's involved in dozens of projects all over the world with decades of buildings blurred in his head, had a very succinct, knew exactly what he was talking about from 2 weeks ago. And he made a point to me after that meeting, not in front of the client, to say, you should always out-prepare me in a meeting. There's no way that I should be coming in and just know the answer to a question when you're the project manager. So that kind of resonated with me, to learn to prepare. And there's oftentimes you're going to prepare a lot of material and not an ounce of it gets touched. I'm sure you've all experienced that with whether it's whatever studio projects and people don't appreciate certain aspects of it. but that's the nature of the business. You need to be prepared because people trust you when they realize that you have the answers. And if I never share anything that I prepared, that's okay. I don't get lost in that. I learned a lot from preparing that information, but we need to be proactive and ready with that. And the other piece that resonated was John Picard, the founder of Picard Chilton Architects, made a point of saying in front of the client, like, the reason I love working with MK is I trust them and I don't have to waste my time. When they tell me I can't do something, sometimes with another engineer, I might press on them, like, what do you mean I can't do that? And we have to spend time iterating through something. But when Ron or Matt are sitting here and they tell me this just doesn't make sense, then I can just put it to bed and move on to the next challenge at hand. And that all happened because he has a trust for us that's been built over years of working together. And so these are things that don't happen overnight, but it's a matter of respecting us, respecting what the architect's vision is, and we've executed enough of it that they know that we're trying to realize the vision that you've created, but at the same time, make sure it gets built. And with that, thank you very much.